Welcome everybody to the workshop. I'm really happy that we're doing this. Hopefully, all you guys had a nice trip here. There's a bunch of things to do in Rio, as you may know. Hopefully, this will be a nice event that will motivate a lot of research and new ideas. I had some things to say before we start. Let me go to my checklist. Okay, so what's the purpose? Well, the purpose is to learn some mathematics, especially number theory. And so most of the afternoons are free. This is on purpose, so you guys can discuss, and so the community here can interact and hopefully solve some problems. We will have a cocktail on Tuesday, which just after the short talks. So all short talks will be given by students. So hopefully you guys all can attend and ask questions and make the students nervous and etc. One of my students will be presenting, so please ask a lot of questions. What else? There's a dinner on Thursday. If you want to participate, so you have to go to room 208 and say you want to participate and then pay the fee. You guys all received an email with instructions about it, or you can just reply the email as well. Okay? So it will be about 150 reais. What else? And if you have any questions at any point, please look for me or Ramon, which is right there, or Marco, which is right there. Especially those two, don't look for me too much. What else? I think that's it. Yeah, so let's start. So it's a pleasure to introduce Gugu. It's a researcher here at IMPA. And he will be talking about fractal geometry, the Markov and Lagrange spectra, and the set difference. Gugu, please. Is it turned on?
Alô, alô, funcionou. Okay. Thank you very much, Felipe, Marco, and Ramon for the invitation. Of course, a great pleasure to talk in this wonderful conference. So I'm not really a specialist in number theory, so my official field of research is dynamical systems and some fractal geometry, but I like very much number theory. I have some papers, in particular related to Diophantine approximations, and so I'll talk on some results that are on the confluence of, say, fractal geometry and Diophantine approximations. And so I will start with the most basic problem in Diophantine approximation, that we want to approximate irrational numbers by rational ones, and want to know what we expect for the error, for the quality of the best approximations of a given irrational number. So this is a very classical result that says that so it's proved by Legendre. Dirichlet has a nice proof that gives a little more information, that every irrational number can be approximated by rational numbers with error smaller than the inverse of the square of the denominator. This is not the best possible result that holds for all irrational numbers, but it's close to be the best possible result. And the best possible result that holds for every irrational number simultaneously is this result by Hurwitz and Markov from the 19th century that says that that every rational number has infinitely many rational approximations, P over Q. I always assume that P and Q are integers and Q is positive, with error smaller than 1 over square root of 5 times Q squared. So you can multiply the denominator by a constant larger than 1, the square root of 5, that's slightly larger than 2 indeed. And this inequality always has infinitely many rational solutions. So for every given irrational number alpha, this inequality has infinitely many solutions P over Q. But square root of 5 is the largest constant that makes such a result true. So if you put any constant larger than square root of 5 in the multiplying q squared in the denominator, there are irrational numbers. For instance, the golden mean, for which the corresponding inequality will have only a finite number of rational solutions. But given an irrational number alpha, you can search, you can try to find the best possible constant that makes such a result true. So given alpha irrational, so this is the inequality given by Legendre's Dirichlet's theorem. This is the inequality given by Hurwitz's Markov theorem. But in general, we can try to find the largest constant k for which such that this inequality has infinitely many rational solutions, P over Q. And we call this constant k of alpha. K of alpha is the supremum of the set of constant k, such that this has infinitely many rational solutions. You can write this as a lim sup like this. And, well, this is at least square root of 5 for any rational number. For the golden mean, as I mentioned, it's exactly square root of 5. You cannot improve. But for other irrational numbers, you can try to improve this constant. And so the main character of this talk is the Lagrange spectrum, which is essentially the image of this function. It's a set, indeed more precisely, it's a set of finite values of k of alpha. Finite because k of alpha can be infinite. Indeed, it is infinite for most real numbers alpha. So there is a full Lebesgue measure set of real numbers for which k of alpha is infinite. But anyhow, there are many real numbers such that k of alpha is finite. For instance, they form a set of full Hausdorff dimensions, so Hausdorff dimension 1. And we are interested in finite values of k of alpha. And the set of these finite values is the Lagrange spectrum. We can make so a short version of Hurwitz's Markov theorem is just to say that square root of 5 is the minimum of L. So it's the smallest element of L. And this set encodes many Diophantine approximations of real numbers. And it's a quite interesting set. So it's not very easy to describe. And we'll try to give some information on the topological and geometrical structure of L. The first non-trivial result on L is that the L begins like a discrete set. So it has the smallest element, which is square root of 5, as already mentioned. But it also has a second smallest element, which is 2 square root of 2, a third smallest element, square root of 221 over 5, etc. We have a sequence of minima converging to 3. So 3 is the smallest accumulation point of L. And so L begins discrete. It is not discrete all the time. We can describe in a more precise way this smallest elements of the set L. All of them are given by an expression of this type, square root of 9 minus 4 over z squared, where z appears in a solution of this Diophantine equation, which is called Markov equation. It's an equation on positive integers. And so we can indeed describe all the solutions of this equation in this way. So we have this remark that has this what's so-called Vieta moves, that given a solution, we can find 2 larger solutions. Just by observing that, for instance, this is an equation, this is a quadratic equation in each of the variables. For instance, a quadratic equation on x. So if x is a root of this equation, regarded as a quadratic equation on x, 3yz minus x is also a root of the same equation. So we can replace x by 3yz minus x. And analogously, we can replace y by 3xz minus y. So this gives 2 larger solutions. And of course, you can do the same with z, but typically 3xy minus z will be smaller than z. But anyhow, if they are in this order, so x smaller than y smaller than z, then indeed it's easy to see that these 2 solutions are larger than the previous one. If we start with the smaller solution, the smallest solution, which is clearly 1, 1, 1, 1 plus 1 plus 1 is 3, no? Then you can apply these operations. Well, here x equal to y and you have only one solution. Still, you have x equal to y, you have only one solution. But from now on, it's not difficult to see that all terms of every solution are different, so every solution will give birth to two new solutions, and from 1 to 5 on, we will have a true binary tree of solutions. And it's not difficult to prove using a kind of Fermat descent argument that every solution of this equation appears somewhere in this tree. So this tree indeed describes all the integral solutions of this equation. So there is a classical open problem related to this, that is Frobenius unicity problem. The question is whether the Z, so largest element of a triple, determines the triple of a solution of Markov's equation. So the question is whether is this possible to have two different solutions with the same maximum element, and the standing conjecture that is not possible. This would have a consequence on this function k of alpha. So it says that if this is true, then the pre-image of any element smaller than 3 belonging to the Lagrange spectrum should be a single equivalence class of irrational numbers, where the equivalence relation is given by this action of GL to Z by via Möbius transformations. And this can be described in terms of continued fractions in a better way. So two irrational numbers are equivalent if and only if their continued fraction representations coincide after some point modulo translation in the index. So, yeah. Well, what is true and does not depend on this conjecture is that the pre-image of every element of the Lagrange spectrum smaller than 3 is a finite union of equivalence classes of irrational numbers by this relation. It's not difficult to see that if alpha is equivalent to beta, then k of alpha is equal to k of beta. It will be a consequence of a formula for k of alpha that I will show you a few slides later, but it can also be proved directly. So, okay, but so as I mentioned, Lagrange spectrum starts like a discrete set, but it's not discrete all the time. Indeed, it ends by a whole half-life. And this was proved by Marshall Howe in 1947 in a paper in Annals of Mathematics. But indeed, his main statement was about sums of continued fractions, not quite on the Lagrange spectrum, but his statement implies that the Lagrange spectrum contains a whole half-line. Indeed, what he proved, his main result, is the following. You consider the set C4 of all numbers in the intervals 0, 1 that can be written in continued fractions using only coefficients 1, 2, 3, and 4. It turns out to be a Cantor set, so the homeomorphic of Cantor set is what we call a regular Cantor set. I will talk in the next slides on regular Cantor sets, try to give an idea of, in general, what is a regular Cantor set. But C4 is an example of a regular Cantor set. And so the result says that the arithmetic sum of C4 with itself, so the set of all sums x plus y, where x and y belong to C4, is a whole interval. It's a lot. That starts with 0.4 something and ends with 1.6 something. So it's an interval of size larger than 1. And this can be used, so together with a relatively elementary formula for k of alpha, to prove that the Lagrange spectrum contains a whole half-line, say 6 infinity. 6 infinity is not the largest half-line contained in the Lagrange spectrum. The largest half-line contained in the Lagrange spectrum was found by Freiman in 75. It starts with this nice quadratic irrational, so it's nice algebraic number, which is approximately 4.5278, etc. So these two results, as I mentioned, are related to regular Cantor sets and to the study of sums of regular Cantor sets, which is a subject that also appears naturally in dynamical systems. And we'll see the relationship of this with the Lagrange spectrum soon in the next slides. But first of all, what are regular Cantor sets? Regular Cantor sets are what we call in dynamical systems hyperbolic sets of dimension 1. So they are maximally invariant sets for some expanding maps, so differentiable maps with derivative always larger than 1 in absolute value, defined in some finite union of intervals, and have some combinatorial restrictions, but they have nice geometric properties, so they are kind of self-similar in the sense that very small parts of a regular Cantor set are diffeomorphic to the whole set or to large parts of the whole set with uniformly bounded distortion. So this is important. And a particular case of regular Cantor sets that is particularly important for this theory, for understanding Markov and Lagrange spectra, are the regular Cantor sets which are defined by this map. So the dynamics will be always the Gauss map, which is just fractionary part of 1 over x. That is a map whose dynamics is very much related to the continued fraction representation. And, well, you have a single dynamics, but you have infinitely many Gauss Cantor sets because you have infinitely many ways to choose the domain of the map. So you can restrict the Gauss map to some finite unions of intervals and consider the maximally invariant set. For instance, if you restrict to 1/5 1, then it corresponds to, so let's show a graph of Gauss map. This is fractionary part of 1 over x. So if you consider just the 4 last branches, so the restriction to 1/5 1, the set of points in 1/5 1 such that you can apply this map infinitely many times, and you always remain between 1/5 and 1 is exactly the set C4 that I described earlier. So C4 is a Gauss Cantor set. And of course, you can take, say, the n last branches of this map. You have the corresponding set Cn, which is also a Gauss Cantor set. But you have more complicated Gauss Cantor set. For instance, set of points that only have 1 and 2 in continued fraction, so that correspond only to the 2 last branches, but some patterns like 1 to 1 are forbidden. Say, consider sets of continued fractions where you only have 1 and 2, but you don't have 1 to 1 as a factor of the continued fraction as a subset of. So you don't have 3 consecutive terms which are 1 to 1. And this is also a Gauss Cantor set, which is a more complicated combinatorics. But, so then, perhaps the simplest example of a regular Cantor set is the usual ternary Cantor set, a set of points that have only digits 0 and 2 in base 3, that you know well in the interval 0, 1. It's the maximal invariant set of this map, that is 3x between 0 and 1/3, and 3x minus 2 between 2/3 and 1. So the set, and it's not defined between 1/3 and 2/3. The set of points such that you can iterate this function, and you are always in the domain, so you never go to this hole between 1/3 and 2/3, is the usual ternary Cantor set. It's perhaps a good exercise, but it's not difficult to see that. So the usual Cantor set has this dynamical structure, and this is a perfectly self-similar set. So small intervals of the, so if we intersect this Cantor set, say with 0, 1 over 3 to the n, this is similar. So we have a homotopy that sends this to the whole Cantor set, the ternary Cantor set. So this is a common feature of regular Cantor sets, but in general we don't have an exact homotopy, but exact similitude, but we have a diffeomorphism with bounded distortion that replaces this. In the case of Gauss Cantor sets, we always have a Möbius transformation with bounded distortion that sends small parts of the Cantor set to the whole set or to large parts of the whole set. Okay. So this is the continued fraction representation of alpha. So why this is related to the dynamics of Gauss map? In the same way that, say, decimal representation are related to the dynamics of a map from 0, 1 to 0, 1 that's given by fractionary parts of 10x. So you have the question, so if you have a real number and to make a representation using integers, the first non-trivial information is what is the integer part. Every real number is between k and k plus 1 for some integer k. K is the integer part of your real number. So you can write your real number as k, an integer, plus a number between 0 and 1. And the question is what we do when you have a number between 0 and 1. So the answer of decimal representation is that we multiply the number by 10. And then you get a number between 0 and 10. And the integer part now is a non-trivial information, which gives the first digit. You remove the integer part, you are again between 0 and 1, and you multiply by 10. You remove integer part, multiply by 10, etc., and the sequence of integer parts is the sequence of digits. So the answer of continued fraction representation is that when you have a number between 0 and 1, you take the inverse of the number, which is a number larger than 1 now, and the integer part gives a non-trivial information, which is the first coefficient, say. Then we remove integer part, you are between 0 and 1, we invert, remove integer part, invert, so you are iterating Gauss map, and the sequence of integer parts of coefficients gives the continued fraction representation. So continued fraction has a lot to do with the dynamics of Gauss map. So this is the notation for continued fraction representation. And, well, we have this elementary formula for k of alpha. It's elementary because it's a corollary of a very elementary equality relating alpha with the convergence of the continued fraction. But here, alpha n is the forward continued fraction. an plus 1, an plus 2 started with an. The inverse of alpha n are the iterates of fractionary part of alpha by Gauss map exactly. So inverted, we have this alpha n. Alpha n plus 1 minus 1 is g of alpha n minus 1. So, and beta n is a rational number between 0 and 1. It's the backward continued fraction starting with 0, an minus 1, an minus 2 up to a1. And we can prove that this is equal to qn minus 2 divided by qn minus 1, where the qn are the denominators of the convergence of alpha. Indeed, here. And here we have an exact formula for the error of the approximation of alpha by Pn over Qn, where Pn over Qn is just the truncated continued fraction of alpha, starting with A0, going up to An. So this is always a rational number, of course. And the error is always smaller than 1 over Qn squared, as you see. And the coefficient that multiplies Qn squared is exactly alpha n plus 1 plus beta n plus 1. So k of alpha is the lim sup of these coefficients here. Because the convergents are the best possible rational approximations of alpha, in the following sense, that all of this is very elementary, but very, very strong. So we have this kind of miraculous theory of continued fraction that gives, by a simple dynamical algorithm, all the really good rational approximations of a given number. So the first fact says that at least one between two consecutive approximations from the continued fraction has errors smaller than half of the inverse of the square of the denominator. And the second fact says that any rational approximation with this property needs to be a convergence of the continued fraction of alpha. So it needs to be equal to Pn over Qn for some n. So really all the good approximations of alpha come from the continued fraction. So if you want to estimate k of alpha, you can restrict your attention to the convergence Pn over Qn. This is why we have this formula. But this formula of lim sup of alpha n plus beta n can be interpreted, as did Perron, as a dynamical formula for k of alpha. We can consider a more abstract phase space. So this set of sequence of B infinite sequences of positive integers. And it's a good place to do symbolic dynamics. You consider, so all these sequences, and you have a shift map which just changes the middle of the sequence, so where is the term A0? So the sigma of a sequence AN is a sequence Bn, where B0 is A1, B1 is A2, B minus 1 is A0, etc. So Bn is An plus 1 for every n. So we are just taking the sequence and say, doing one step to the left. In the sequence, this dynamics doesn't seem to be to make much changes in the sequence. Essentially the same sequence, you just move at the central position, but this is indeed a very rich dynamics. It has infinitely many periodic points of every period. It has dense orbits, etc. So here we have this dynamics, or the shift map, and you can define a real function, so a potential or an observable, etc. A real function defined in this phase space, which is just the sum of the forward continued fraction A0, A1, A2, etc., plus the backward continued fraction 0, A minus 1, A minus 2. And if you consider f of sigma n of theta, so you apply the shift map n times, and then you compute the function, it gives alpha n plus beta n, where alpha n is n plus 1, n plus 2, etc., and beta n is 0, n minus 1, n minus 2. Well, before you had a finite continuous fraction, here you have an infinite continuous fraction, but the difference becomes exponentially small. So the set of these lim sups of alpha n plus beta n gives exactly the Lagrange spectrum n. So the set of finite values, indeed, of this, it can be infinite. So we have this dynamical characterization. So we have a dynamical system in a real map. You associate this set, which turns out to be the classical Lagrange spectrum. But you can do this in much more generality. So always when you have a dynamical system and a real function, you can associate a dynamical Lagrange spectrum as the set of the lim sup of the function in the orbits of the map. And indeed, the Lagrange spectrum is a particular case of a dynamical spectrum associated, say, to a geodesic flow in the modular surface. Or interesting parts of the Lagrange spectrum are also dynamical spectra associated to Hochschuss, so to hyperbolic sets in dimension 2, but I will not talk much more on this now. But anyhow, there are natural dynamical generalizations of the Lagrange spectrum. There is also an important set that is in the title, but I'm mentioning only now, that is the Markov spectrum, that has a very simple dynamical definition compared to the previous one. We just replace lim sup by sup. We have the set of limits of the functions. What is this? No. Okay. We have the set of the supremum of this real function on all orbits of this map. So, but this set also has a classical, nice arithmetical interpretation. It's just related to indefinite quadratic forms in two variables. So consider forms ax squared plus bxy plus cy squared. A, b, c are real numbers. And I'm assuming that the discriminant is positive. Here, indeed, I'm assuming that the discriminant is 1. But in general, if it's positive, you just multiply this by the square root of the discriminant, and it gives the same thing. So I'm just normalizing the discriminant to be 1. And you consider the set of the infimum of the norms of these quadratic forms on integer points, which are not both 0, so integer points different from 0, 0. And the set of these infima, or the inverse of this infima, give the classical Markov spectrum. And from this dynamical characterization, it's not difficult to see that M and L are closed sets in the real line, and that the Lagrange spectrum is contained in the Markov spectrum. Well, in order to state the next results, we need the notion of house of dimension that is defined in one line here. It's related to good coverings of metric space by small balls. The idea is that and you have an exponent. If the exponent is very large, then you have good covering such that the sum of the radius of the covering to this exponent S can be arbitrarily small. So if S is large, this infimum is 0. And the infimum of the large values of S is the house of dimension. It's possible to prove that if S is smaller than the house of dimension, then this sum tends to infinity, even for the best coverings when the radius tends to 0. And you have only one, so limit exponent, which is the Hausdorff dimension of X. This is a natural tool to estimate the size of, say, of sets of zero Lebesgue measure of the real line or of fractals in any dimensions, etc. That's a very classical notion. And so regular Cantor sets in particular are typically sets of zero Lebesgue measure on the real line, but which have fractal structure. And there are regular Cantor sets which are much larger than others. For instance, C4 is much larger than C2. If you C2, you only have 1 and 2 in the continued fraction. C4, you have 1, 2, 3, and 4, for instance. And the Hausdorff dimension is indeed larger of C4. And so we prove the following. So same Marshall-Hall proved that, for instance, up to, if you intersect Lagrange spectrum with minus infinity square root of 10, which is 3.16 something, then the set is already uncountable. But it has zero Lebesgue measure, and in this Hausdorff dimension smaller than 1. And it's natural to do this in general. So you take a half line, minus infinity t, and intersect with the Lagrange spectrum. You can also intersect with the Markov spectrum, and it turns out that the Hausdorff dimension of these two intersections is always the same. We call this d of t. And d of t is a continuous function whose image is the whole interval 0, 1. It doesn't seem very interesting fact, or a special fact that a given function is continuous. But in this case, it's not trivial, because if you do this, say, with the usual ternary Cantor set, you intersect with a half line and compute Hausdorff dimension. This is a kind of boring function, because if t is at most 0, the intersection is empty, so dimension is 0 or minus infinity, depends on the definition. But so dimension is 0, say. But if t is positive, then the intersection already contains a homothetic copy of the whole set. So the Hausdorff dimension is already the Hausdorff dimension of the full set, which is log 2 over log 3. So this function, the Hausdorff dimension of intersection of the usual ternary Cantor set with minus infinity t, only has two values, 0 and log 2 over log 3. It's not a continuous function, but here it is a continuous function. Given any number between 0 and 1, say pi over 4, there is a half line whose intersection with the Lagrange spectrum has exactly the dimension pi over 4, for instance. And this is a non-trivial fact, so this means that the Markov and Lagrange spectrum have a kind of multifractal structure or something like this, which is not very usual even for fractal sets. I have other information on this function. It's minimum between 1 and twice the Hausdorff dimension of the pre-image of minus infinity t by the function k of alpha. This says that immediately after 3, d of t is positive. So between 3 and 3 plus epsilon, the Lagrange spectrum already contains small Gauss Cantor sets with positive Hausdorff dimensions. Before square root of 12, the dimension is already equal to 1. Square root of 12 is 3.46 something, but as you'll see, much before this, the dimension is already 1. So this is an impressionistic drawing of the Lagrange spectrum. So it starts discrete, so you have a smallest element, second smallest element, etc., converting to 3. Then you contain a whole half line starting here. In between 3 and, say, square root of 12, or between 3 and 4.52, the Lagrange spectrum has a nice, complicated fractal structure, so it passes through every Hausdorff dimension between 0 and 1, etc. We also prove in this work that Hausdorff dimension of pre-images of single points t, for large values of t, the dimension not only is positive, but tends to 1 when t tends to infinity. So k of alpha is strongly non-injective for large values of the functions. Also, L has a lot of isolated points. For instance, square root of 13 is an isolated point. All points smaller than 3 are isolated. If you remove the isolated points, then it gets a perfect set. So you don't have isolated points of second order, etc. So L prime is equal to L2 prime. We proved that indeed this dimension of K, for instance, for every t in the Hall's ray, so in this half line content, this function d of t restricted to the Hall's ray will be strictly increasing And d of t, so big D of t, will coincide with the Hauser dimension of k minus 1 over t. So this is a continuous function for t, say in the Hall ray or in any interval contained in the Lagrange spectrum. Lagrange spectrum probably contains a lot of intervals before the Hall ray, but it's still not a theorem, so we don't have a result. But there are many conjectures in this direction. So, this is a collaboration with Christian and Silva Villamil, a former PhD student of mine, and now in China, in Shenzhen, Sustek. So, these are true pictures of the Lagrange spectrum. So, so we made an algorithm with Carlos Mateus and Vincent Delecroix to approximate the Markov and the Lagrange spectra to any given precision. So here we have a precision like smaller than 10 to the minus 5 for the Lagrange spectra, up to square root of 12. After square root of 12 is more difficult, but it seems to contain large intervals here. Indeed, there is a conjecture by Bernstein that says that it at least should contain 4.1 up to 4.5, but this is up to 4.52 indeed, but this is still open. What is known that it contains everything after 4.5, 7, 8, etc. So the Hall ray. This is not a true gap because here we don't have, we only consider coefficients 1, 2, and 3. And when we consider 4, we have a gap close to attached to the Hall ray, but it's much smaller. So the size is smaller than 10 to the minus 7 and cannot be seen as large as this. But anyhow, this is a very good approximation of the true picture. So this is an asymptotic result. So we are in an analytic number theory seminar, so you should have some log results. So this is an asymptotic expression for the house of dimensions, for d of t, for t close to 3. So for the small value. So d of 3 is 0, because up to 3 the set is countable. We start to have Cantor sets immediately after 3, and d of 3 plus epsilon is positive, and is asymptotically given by some expression like, well, you can start like this, but the best expression involves Lambert function, which is the inverse of x times e to the x. You can have approximation, an arbitrary number of terms in the asymptotic expression. But we have an error term, which is order of log epsilon divided by log epsilon square. And this error term is optimal in a precise sense. If you have a better approximation, so any function, any C2 function, which gives an error which is little o of log epsilon divided by log epsilon square, then this function needs to be strange. Its second derivative needs to change sign infinitely many times close to 3. So it should become kind of irregular. So of course, you can approximate by C-infinity functions with arbitrarily small error asymptotically, but in an artificial way. So we have a natural, nice function. So whose second derivative has constant sign in a neighborhood of 3, then the error term is at least this, because this function has this function d of 3 plus epsilon has quasi-plateau, so sets where the function is essentially constant. And the expected variation in an interval of the sizes would be much larger in some sense. So if the function is very regular, then the error cannot be smaller than this, kind of. So we have a kind of optimal result for the asymptotic of d of 3. So this is not a Helder continuous function at 3. And this is almost tautologic, because this function d of t needs to grow in a set of very small halves of dimension by its own definition. And a Helder function cannot grow, so the image of a set of very small halves of dimension needs to be to have 0 Lebesgue measure, to have halves of dimension smaller than 1. But here the image by d of t of sets of arbitrarily small halves of dimension can be non-trivial intervals. So it cannot be held at least at 3, and indeed it's not, so have this. We have graphs of d of t. Indeed, we have two approximations, and a lower approximation in red, an upper approximation in blue. Here you almost don't see red and blue. They have good approximation. So together with Carlos Martin and Paulina Vitnova, we have this approximation of the graph. So we have a lot of plateaus, as I mentioned. So intervals where the function is constant. Also have quasi-plateaus where the variation is very small and larger in some sense. Here, as you see, so d of 3 is 0, and the function is continuous. But here you see 0.4, 0.5. So it grows very quickly close to 3. D of 3 plus 10 to the minus 6 is already larger than 0.13 or something like this. So it grows really, really fast close to 3. But it's continuous. It tends to 0 and it tends to 3. You cannot see in this. So let T1 the smallest point where the dimension is 1. So together with David, who is there, we conjectured that the Lagrange spectrum should contain intervals immediately after T1. So the interior of L intersected at T1 plus delta should be non-empty for every delta. But this is open. Indeed, as I mentioned, it's open whether there is any interval before the Hall's ray, so before 4.5 or something like that. But T1, we know more or less what is T1. We know T1 with 6 decimals. Because we know that T1 belongs to this interval. It's like between 3.334384 and 3.334385. So the decimal representation of T1 starts with 3.334384. And the conjecture so implies that in this interval of size 10 to the minus 6, the Lagrange spectrum should have non-empty interior. The Hausdorff dimension of L, so up to 3.334384 is smaller than 1, so the Lebesgue measure is 0 of this intersection. But the Hausdorff dimension up to 3.334385 is already 1. This is a theorem, but what is not known is whether it has non-empty interior, and also not known whether it has positive Lebesgue measure. Of course, if it has interior, it has positive Lebesgue measure, but we don't know either. So this is a picture of Jean-Christophe Yokoz. It was my postdoc advisor. So I was a student of Jacob Palles here at IMPA. He gave me a thesis problem related to some arithmetic sums of regular Cantor sets, but not motivated by the Lafontaine approximations, but by homoclinic bifurcations in dynamical systems, which is a subject that seems quite different from number theory, but indeed the same kind of problems related to sums and intersections and arithmetic difference of regular Cantor sets appear naturally in this context. So Jacob wanted me to try to prove a conjecture by himself. I made some progress in my thesis, but indeed we only solved this problem and proved the Palles conjecture in the postdoc in collaboration with Jean-Christophe. And the techniques of this proof were very important to the previous results I mentioned on the continuity of the Hausdorff dimension of intersection of Markov and Lagrange spectra. So what was Palles conjecture? So you have, this is the definition of arithmetic sum and arithmetic difference of two sets of the real line. In particular of two regular Cantor sets, but it could be any two sets. Here, so sum is the set of all sums, x plus y, x and k, y and k prime. Difference is the set of all x minus y. And the difference has this kind of physical interpretation. You can think that you have these two sets, k and k prime, but k prime is fixed, and k is moving with constant speed. So you have k prime and k plus t. And no, the converse. So k is fixed, and you have k prime plus t. K prime is moving. The set of values of t for which these two sets have non-empty intersection is precisely the arithmetic difference. Because if they intersect, you have x in k, y in k prime, such that x is equal to y plus t, so t is x minus y. So t is in the arithmetic difference. So the conjecture of Palles essentially says that if the sum of the Hausdorff dimensions of two regular Cantor sets is larger than 1, then the arithmetic difference typically has non-empty interior. If the sum of the dimension is smaller than 1, then this difference has also Hausdorff dimension smaller than 1, and so 0 Lebesgue measure. It cannot have an interior. The conjecture is that when the sum is larger than 1, then we expect to have non-empty interior. Indeed, we proved this with Yokoz. We proved that typically the interior is dense in the arithmetic difference. it has some consequences on homoclinic bifurcations. But anyhow, a consequence of the techniques of the main technical lemma of my work with Yakovs is this dimension formula that I only state in the case that is relevant for us, that's for Gauss Cantor set. The Hausdorff dimension of an arithmetic sum of two Gauss Cantor sets is always equal to the natural upper bound, which is the minimum between 1 and the sum of the Hausdorff dimensions of the two sets. And this is the main technical lemma used in the proof of, also with a lot of combinatorics and etc. So that is important. So all the previous results and even the pictures of the Markov and Lagrange spectra up to now are coherent with the possibility that M and L are the same sets. Indeed, they are very similar sets. They coincide up to 3. They coincide after 4.52 something. And the Hausdorff dimension of the intersection of both sets with any half line is always the same. The Hausdorff distance is very small because in the picture, the precision 10 to the minus 5, you don't see any difference between them. And so, indeed, there is an old paper claiming that they are equal, but with a wrong proof. Proof is wrong because it's false. Indeed, they are not the same set. They are different. The first example of an element of M minus L is also due to Freiman in 68. He gave this explicit algebraic number here, which belongs to M minus L. Freiman gave other example, for instance, this alpha infinity, which is indeed an accumulation point of M minus L. So it's accumulated, also an algebraic number, and it's accumulated by the sequence of algebraic numbers belonging to M minus L. These sequences are exhibited by Mary Flahaev in 77. Okay, so up to now we know that M minus L is infinite, and non-empty in particular, but we don't know whether it's large. It could contain intervals or not. We don't know. But well, another conjecture by Cusick is that after square root of 12, the two sets coincide. So, but this is, so in collaboration with Carlos Mateus, we gave, you could reach a more precise understanding of the fractal structures of M minus L. M minus L has indeed 0 Lebesgue measure, indeed Hausdorff dimension smaller than 1, but it has positive Hausdorff dimension, indeed Hausdorff dimension larger than 1/2, for instance. We improved these estimates in collaboration with Mark Polycott and Polina Vitnova, so the dimension is smaller than 0.8, for instance. So it's slightly larger than 1/2. But we can improve, later we could improve this bound, but not this is still the best upper bound known on the dimension of M minus L. Also in collaboration with Carlos Mateus, we disproved Cusick conjecture. We exhibited some elements larger, quite larger than the square root of 12 in this difference, M minus L. In collaboration with Harold Rasso, who is there, and Carlos Mateus and Luc Jeffrey, we proved that indeed how the dimension of M minus L is larger than 0.594, almost 0.6, but not quite. And we also exhibited some larger elements. So this, as far as we know, is the largest known element in M minus L. It's slightly larger than 3.942. And we have regular Cantor sets close to this number with dimension larger than 0.594 contained in M minus L. We also found some small elements in M minus L, so close to 3. 3 is the smallest possible thing, but up to 3, the two spectra coincide. So this one is small, M4, for instance, smaller than 3 plus 10 to the minus 6. I think as far as I know, it's the smallest explicit example of an element of M minus L, but we can find more because in this work we conjecture that 3 belongs to the closure. So the infimum of M minus L should be 3. And I'll talk more on this in a few slides. But we also prove in another paper that M minus L is not closed. We proved that We couldn't prove at this point that 3 is in the closure of M minus L. 3 belongs to L, of course. But this point, 1 plus 3 over square root of 2, so it's approximate 3.12 something, belongs to this intersection of L and the closure of M minus L. So L is a closed set, M is a closed set, but M minus L is not closed. So the closure of M minus L intersects L. There is a combinatorial concept that is related to all these examples of points of M minus L. That's the notion of semi-symmetric, non-semi-symmetric finite words. A word on a finite alphabet here, the alphabet will be always contained in 1, 2, 3, is semi-symmetric if you consider the periodic sequence with period alpha and the transpose of it, so the periodic sequence period alpha t, where alpha t is just the transpose of alpha, so if alpha is A1, A2, AN, the transpose is AN minus 1 up to A1. If these two sequences are essentially equal, so if they belong to the same orbit, then we say that the sequence is semi-symmetric. It's equivalent to say that the sequence is the concatenation of two palindrome words. Okay, if the word, so all the examples of points in M minus L are related to sequences which are not semi-symmetric and have odd length. Indeed, the first Freiman example is related to this sequence. The second Freiman example is related to this sequence. My example with Mateus, which disproves Kuzik conjecture, is related to this sequence. So we have large examples of points in M minus L related to these two sequences, this with Luke Jeffreys and Carlos Mateus, this with Luke Jeffreys and Harold Eraso, so the largest example of point in M minus L is related to this sequence. These points close to 3 in the Lagrange spectrum are related to points in this sequence. So these 4 examples are related to k equal to 1, 2, 3, 4, but we have candidates for points in M minus L which converge to 3, but we could not prove that they really belong to M minus L. But here is the sequence of points that converge to 1 plus 3 over the square root of 2 that we use it to prove that M minus L is not closed. And how we associate elements of M minus L to odd non-semi-symmetric sequence? Well, you consider periodic sequence. So you have alpha such a sequence. You consider a periodic sequence with period alpha and a periodic sequence with period alpha t. And you want to connect them. So the Markov value, the lim sup or the sup of the alpha n plus beta n for both sequences is the same because they're essentially so they have this symmetry. But if you want to start with this sequence and then change a little the sequence and then end with this sequence, then the Markov value necessarily will grow up by at least a positive constant that depends on alpha. Because any modification you do in such a sequence will make increase. So the maximum is attained in some position here, but also in some position here because the thing is periodic. And the size of alpha is odd. So if you change a number here, 1 becomes 2 or things like this. If you decrease the value here, necessarily you increase the value here in the previous period. So any change you make in the sequence will increase by a definite value the Markov value of the sequence. But if you want to connect alpha with alpha t, you have a problem like this. You want to modify things like this and connect. If you want to connect alpha t with alpha, the problem is like this. It's a different problem, combinatorial. And typically the answer is different. And in one direction, it's cheaper to move from the one beginning of the sequence to the other sequence, and it's more expensive on the other side. So you can connect from one side and not to the other. It's a question related to the notion of transitivity in dynamical systems, and indeed it gives examples. If you connect in the cheaper way, you have a sequence where the supremum is a maximum, is attained in the middle. It's not the lim sup. The lim sup, when you tend to plus infinity or minus infinity, is the same and it will be smaller, strictly smaller than the Markov value. And And you cannot connect in the other way. So it indeed will not belong to the Lagrange spectrum. So there is a construction of points in M minus L that are inspired by this dynamical notion of transitivity. In this case of a partial breaking of transitivity, break the transitivity in one direction but not in the other. Well, here we have a more recent result that I want to kind of announce here. We are quite confident that in a finite time, perhaps 1 month, we'll have a paper on archive on this in collaboration with Davi, Harold, Carlos Mateus, and Samuel Vieira. We think we know how to prove that infimum of M minus L is indeed equal to 3. And the idea is to use techniques developed in this paper that was recently published in GEMS that gives this asymptotic formula for a dimension of L up to 3 plus epsilon that describes the structure of the Lagrange spectrum. There are many types of sequence that can appear close to 3. They have a very nice combinatorial description related to the notion of renormalization. So there is a very nice paper by Bombieri in Esposiciones Mathematicae is explaining the proof that of this Markov theorem that characterizes the number smaller than 3 in the Lagrange spectrum, but it also has consequence for numbers after 3. You have a kind of reflection principle that we developed. So the combinatorial of the sequence close to 3 is very interesting, it's non-trivial, but you have a prevalence of the sequence of this kind, which is much simpler than the general sequence that can appear, but most finite sequence of a given size that can appear close to 3 are of this kind, large powers of 1, so 1, 1, 1, 1, 2, 2, 1, 1, 1, 1, 2, 2, with large blocks of 1s. The size should be at least of the order of log epsilon. So you are sequence that give Markov values between 3 and 3 plus epsilon. And you can use this, and this identity, 3 is a special point in particular because there is this identity of continuity. So there are much more sequence with Markov value 3 that you can expect in, say, dynamical perturbations of the usual Lagrange spectrum. There is a special thing on classical spectra related to this identity. It's elementary, but it has profound impact on this theory. And we have, well, a sketch of the ideas of using to prove this. We consider an explicit regular Cantor set, so large blocks of 1 to 2, large blocks of 1, but the size of the blocks between to this interval, R and R plus little o of R, but the little o of R is explicitly this. So the size of the blocks are something between R and R plus R over square root of log R. And this is a Gauss Cantor set, and you are concatenating. It can be described as a kind of Bernoulli Cantor set given by iterations of the Gauss map in a finite union of intervals, and you combine freely. So, but it's a Cantor set with small Hausdorff dimension, and we want to prove that the image of so that the arithmetic difference k minus k is essentially injective. So if you consider the image of k times Cartesian product k times k by this map, the image is k minus k, is the arithmetic difference. And we want to prove that this projection is not exactly injective, but almost injective in some precise sense. And this is useful because you can use this identity in order to relate 3 plus the arithmetic difference with M minus L. Indeed, we want to find elements of M minus L in this difference. So the diameter of k is very small. So k minus k is contained in a small, exponentially small neighborhood of 0 if R is fixed, so exponentially small in R. So if you prove that for every R there are elements of M minus L in this set, then we are done. So we do a kind of inductive construction. We show that most rectangles in the projection of k plus of the first step. When you have a product of regular Cantor sets, you have steps of the construction which are products of finite unions of intervals. So finite unions of rectangular blocks. So it's the first step of a Cartesian product of two Cantor sets. And then you refine these. You have second step like this, and etc. But each step is a finite union of rectangles. In the intersection of these rectangles will be a product of Cantor sets. So we show that most rectangles, for most rectangles in the first step, the projection is injected. The projection of a typical rectangle does not intersect the projection of any other rectangle. And we iterate this, so we look inside every rectangle, we have a problem that is essentially equivalent to understand k minus a constant times k, and the constant is a ratio of power of algebraic numbers, up to an exponentially small error. So we do this a finite number of steps, but which is not very large. It's the square of log epsilon. This is the number of steps we will consider, and we want to prove that the projection is injective up to these steps. And here we use Baker's theorem on linear formulas on logarithms to prove that these projections are essentially injective in all scales. So there are some arithmetic considerations related to the fact that the ratios are essentially algebraic, so related to the golden mean, etc. And here, so we have a lot of other combinatorics, but most sequences are of this kind. So we have a kind of probabilistic method argument, like Erdős probabilistic method, to show that most candidates of points close to 3 in the Lagrange spectrum are of this type, difference of sequence of 1 to 2. So we can, after using this probabilistic method, we can restrict our attention to the arithmetic difference of these sets. And then we use this construction in this number of steps to construct candidates for large, odd, non-semisymmetric finite sequence of this type, large powers of 1, 2, 2, large powers of 1, 2, 2, etc. So corresponding to rectangles in this step of the construction of this Cantor set. Here we have and we use these more or less in this way to construct elements of M minus L. I don't have time to give more detail, but I can show a picture of this product. This Cantor set is very small. The intervals are exponentially small. They converge to well, they are finite, but if you consider infinitely many, both points will converge to phi minus 1 here. And they are exponentially small. Essentially, they are these sets are very close to geometric progressions converging to these points of ratio minus phi minus 2, something like this. And we use these in the estimates. We also conjectured that so at least up to T1, which is the first point where the dimension gets 1, probably the set L prime, the set of accumulation points of L, will be contained in the closure of M minus L, up to T1 at least. Because we have an algorithm of constructing elements of M minus L related to odd sequence that seems to work essentially always if the point is smaller than T1. After T1, we have problems because we could have intervals and could have many redundancies in the representation of. But before T1, we expect a kind of injectivity that supports this conjecture. This conjecture would imply that the house of dimension of M minus L should be smaller than the box dimension of M minus L that should be equal to 1. The closure will contain this intersection, which has house of dimension 1 by definition. So we conject that non-semisymmetric works, so that the corresponding periodic sequence has a value smaller than T1, should produce non-trivial elements and even Cantor sets contained in M minus L. But okay, here we also have a conjecture for this should be a theorem, consequence of this theorem on the infimum of n minus L being equal to 3. So this is the same, this is the half of the asymptotic estimate for d of t. So it's the dimension of m minus L up to 3 plus epsilon should be of this order, but indeed we know how to prove that at least this, and work in progress in collaboration with Christian Silva Villamil, we think that we will prove this equality. So we have an asymptotic estimate which is less precise than those for d of t, but it still is reasonably for the Hauss dimension of m minus L up to 3 plus epsilon. This is related to the upper bound. The lower bound will have essentially the same estimate divided by 2. No? Okay, so I think there's a lot of references. So this is a classical book by Kuzik and Flahaeva, Markov and Lagrange spectra from '89. Well, now we have a newer book with Sérgio Romagna, Davi Lima, and Carlos Mateus that appeared in World Scientific on classical and dynamical Markov and Lagrange spectra. A lot of recent papers on these results. I have this paper. So this is the paper which has those results on how the dimension of intersection with half lines. And okay, so papers by Pallas and Itiokos that related to these conjectures. Okay, this is a classical book by Pallas and Takens on homoclinic bifurcation that also has it. So thank you very much. I'm sorry for the delay.